As you can see here, our unfortunate volunteer Andrew has put himself in a bit of a bind. Make sure to read contracts before you sign them, guys. He has to stop both James on a skateboard, who's 60 kilograms, flying at him at 5 meters per second, and this massive car that's 1,000 kilograms, going at him at 5 meters per second. And we all know that James is going to be easier to stop. But why? Why is James easy to stop? To answer our prior question about why it is easier to stop a skateboard compared to the car, we must learn about momentum, because that right there is the key. If you remember from earlier, we had different masses on our objects. The skateboard was 60, and the car was 1,000. And to get the momentum of an object, you do mass times velocity.
The formula for momentum is simply mass times velocity. If an object has a constant velocity, then its momentum will also be constant. Let's talk about why if the net force is zero and acceleration is zero, then momentum is constant. Average acceleration is defined as a change in velocity over a change in time. The only way to change an object's velocity is to apply some force on the object at any given time during the interval. If no force is applied, then change in velocity is zero, and 0 divided by anything is also 0. The only way that momentum would not be constant was if both force and acceleration were not 0, because if a force is applied, then acceleration would not be 0, and thus velocity would change, changing the momentum as well.
First, we start off with Newton's second law, net force equals mass times acceleration. Then we could substitute change in velocity over change in time for acceleration, leaving us with mass times the change in velocity divided by the change in time. Then we can simply factor in the mass into the numerator, leaving us with mass times the change in velocity all over the change in time. Then we can substitute the final velocity minus the initial velocity in for the change of velocity and factor in mass to leave us with mass times the final velocity minus the quantity of mass times the initial velocity all over the change in time. Then we can substitute change in momentum in for the numerator, since mass times the velocity is momentum, and that would be the final momentum minus the initial momentum. That leaves us with the net force equaling change in momentum divided by change in time. Then change in time can be multiplied on both sides, leaving us with the net force times the change in time equaling the change in momentum. Impulse can be substituted in for the force times the change in time, since it is the average force over a time period, which leaves us with the impulse momentum theory, that impulse equals the change in momentum.
According to Newton's third law of motion, when one object is imparting a force on a second object, the second object exerts a force equal in magnitude and opposite in direction to the first object. Now we know that the change in momentum is equal to the force times the change in time. Solving for force, we can substitute in change in momentum over time. Some people may think that we are stuck here and we can't simplify any further, but if we realize that the amount of time each object exerts its force on the other object is the same, basically one object can't exert a force if the other one isn't, and they have differing amount of times, then we can multiply both sides by time, leaving us with the changes in momentums. The changes in momentum have to be of equal magnitude and in opposite directions. We can then split this change of momentum up into final and initial momentums, and getting the initial momentums on one side and final on the other, we see that we have just proven the conservation of momentum theorem. The initial momentum is equal to the final momentum.
All my fellas, 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 all my fellas. All my fellas.